From the last few videos, we are studying about the radiation, and in the previous video, we have seen that how the spectral of black body radiations are. The things that are known to us from our previous lectures are the black body used to radiate maximum energy. Black body used to radiate energy at all temperatures, and radiation of black body at any temperature consists of different wavelengths. But the wavelength varies with the emissive power, or the emissive power varies with wavelength. Emissive power of a black body varies with wavelength. With increase in wavelength, the emissive power increases and it reaches to the maximum at particular wavelength, and thereafter, if the wavelength increases, the emissive power goes on decreasing. That has been studied by the experiments performed by Lummer and Penningham. The spectral distribution is like this one. If you take emissive power on y-axis and the wavelength on x-axis, then the radiant power varies with wavelength, and the nature of the graph will be like this one. With increase in wavelength, the emissive power increases and it will become maximum at a particular wavelength. This is not the maximum wavelength, it is the wavelength at which the radiant heat is maximum. This is for one temperature of emitter, and with the increase in the temperature of emitter, the nature of the graph will be similar, but the only thing is that with increase in temperature, there is increase in the radiant power, more heat energy is radiated, and the wavelength for which the maximum intensity of radiation decreases. If we go for one more temperature, higher temperature, the nature of the graph will be like this one. Here again you will see that the wavelength at which the intensity of radiant heat maximum will be different, and it is less than that of the previous one. With this, Wens described an law, and according to Wens displacement law, the wavelength at which intensity of the radiant energy emitted by a black body is inversely proportional to the temperature of the body. This is wavelength at which the maximum intensity of radiant heat emitted by a black body is inversely proportional to absolute temperature of that body. Therefore, this lambda m into the absolute temperature is a constant quantity, and this B has a value of 2.898 into 10 to the power of minus 3 lambda m wavelength. It is in meter and the absolute temperature is in Kelvin. This is the Wens displacement law. Now, this Wens displacement law is able to prove the facts that has been observed by the experiment performed by Lummer and Penningham. Now, with this, we come to know few of the facts about the black body radiation. What are those? The black body used to radiate energy, and the energy emitted by the black body is maximum as compared to the other bodies at the same temperature. This is the one thing. The other thing is that the black body radiation consists of the different wavelengths. The emissive power changes with wavelength. This emissive power is maximum at particular temperature, at particular wavelength. This emissive power is maximum at particular wavelength. The particular wavelength at which the emissive power is maximum for black body is inversely proportional to absolute temperature. And thereafter, one more thing that we stated earlier is that the amount of radiant heat emitted is equal to the area under the curve. मित्रांनो, आपल्याला काही गोष्टी अशा माहित झाल्यात. ब्लॅक बॉडी म्हणजे जे रंगाने ब्लॅक आहे ते नाही, जी बॉडी जास्तीत जास्त हीट ऍब्सॉर्ब करते आणि जी बॉडी जास्तीत जास्त हीट इमिट करते. ब्लॅक बॉडी बाकीच्या बॉडीच्या मानाने जास्तीत जास्त हीट इमिट करते इन द फॉर्म ऑफ इलेक्ट्रोमॅग्नेटिक वेव्स. ब्लॅक बॉडीने इमिट केलेल्या वेव्स ह्या लाईट वेव्स सारख्या असतात, त्यांना वेव्हलेंथ असते. ब्लॅक बॉडीने रेडिएट केलेल्या वेव्स ची वेव्हलेंथ डिफरंट आहे. ब्लॅक बॉडीने इमिट केलेल्या हीट एनर्जीची इंटेन्सिटी ही त्याच्या वेव्हलेंथवर अवलंबून आहे आणि एका विशिष्ट वेव्हलेंथला ही इमिसिव्ह पॉवर किंवा इंटेन्सिटी मॅक्सिमम आहे. ती वेव्हलेंथ लॅम्बडा एम ही टेम्परेचरला इनवर्स प्रोपोर्शनल आहे. आता हे सगळं माहीत झाल्यानंतर ब्लॅक बॉडी हीट इमिट करते कळलं. ब्लॅक बॉडीने इमिट केलेली हीट टेम्परेचरवर अवलंबून आहे हे कळलं. आता प्रश्न असा राहतो की ब्लॅक बॉडीने इमिट केलेली हीट किती असते ते कळणं या कर्व मध्ये असलेल्या एरिया इतकी ती इमिट केलेली हीट असते. एरिया अंडर द कर्व इज इक्वल टू द अमाउंट ऑफ रेडिएंट हीट इमिटेड बाय द बॉडी per unit time per unit area. Stefan Boltzmann Law states that the quantity of radiant heat emitted, this quantity of radiant heat emitted per unit area, per unit time by a perfectly black body is directly proportional to fourth power of its absolute temperature. This quantity of radiant heat emitted per unit time per unit area by perfectly black body, I will represent it by RB. This is the rate of emission of heat by perfectly black body per unit area is equal to this proportionality constant sigma into 10 to the power of t to the power of 4. Sigma t to the power of 4. What this sigma is? Sigma is Stefan's constant. What sigma is? Stefan's constant. And what's the unit and the dimensions of Stefan's constant that we will see? Sigma is the Stefan's constant, and this Stefan's constant sigma is equal to, it is the radiant power per unit area divided by t to the power of 4. Therefore, this SI unit of sigma is, what R is? Heat emitted per unit time per unit area. Therefore, heat, it is joule per unit area per meter square per unit time per second and per Kelvin to the power of 4. Joule per second. Joule is the unit of work or energy, and per second, that is work done per unit time is the power, and therefore I will write it as the watt per meter square per Kelvin to the power of 4. Now, the value of this Stefan's constant, value of this Stefan's constant is sigma is equal to 5.67 into 10 to the power of minus 8 joule per meter square per second per Kelvin to the power of 4. This is the Stefan's law for black body radiation. The quantity of radiant heat emitted per unit time per unit area is directly proportional to fourth power of absolute temperature. This Stefan's law is applicable for ordinary body because the reason is very simple. The emissive power of ordinary body, capital R, it can be compared with emissive power of perfectly black body by emissivity. The ratio of emissive power of a body to emissive power of perfectly black body is the emissivity or the coefficient of emission. Therefore, I will write it as R is equal to E into RB. Therefore, it is E into what RB? RB is equal to sigma T to the power 4, and therefore I will write it as sigma T to the power 4. Only thing is that here you have to add a coefficient of emission here. The value of coefficient of always less than that of the 1, and hence radiant heat emitted per unit time per unit area by any ordinary body is always less than the quantity of radiant heat emitted per unit time per unit area by perfectly black body. This is the Stefan's law of radiation. From this Stefan's law of radiation, we are able to evaluate the loss of heat by any ordinary body when it is kept in a surrounding. Let us consider there is a body whose temperature is more than that of the temperature of the surrounding. Let us consider there is a body whose temperature is more than that of the temperature of the surrounding. Let the temperature of the body, absolute temperature of the body is capital T. The temperature of the surrounding is T0. By Stefan's law of radiation, the quantity of radiant heat emitted, per unit area per unit time by a perfectly black body is equal to sigma T to the power of 4, where capital T is the temperature of the body. This is the heat emitted. Now, we know that when body is kept in a surrounding, it not only emits the heat radiation, at the same time it absorbs the heat radiation from the surrounding. The surrounding temperature has T0, therefore heat absorbed per unit time per unit area is equal to sigma T0 to the power of 4. This is the amount of heat emitted per unit time per unit area, which depends on temperature of the body, and this is the amount of heat absorbed per unit time per unit area, which is equal to sigma T0 to the power of 4. T0 is the temperature of the surrounding. As the temperature of the body T is more than the temperature of the surrounding, it's very obvious that the heat emitted is more than that of the heat absorbed. Therefore, the loss of heat dQ, this is the loss of heat. This loss of heat per unit time per unit area, loss of heat per unit area time dQ by dt per unit area A is equal to sigma T to the T in the bracket T to the power 4 minus T0 to the power 4. This is sigma T to the power 4 minus sigma T0 to the power 4. This is heat emitted and this is heat absorbed. Heat emitted minus heat absorbed, that is sigma in the bracket T to the power of 4 minus sigma T0 to the power of 4, and therefore the rate of loss of heat by a perfectly black body according to Stefan's law of radiation is sigma A T to the power of 4 minus T0 to the power of 4. If the body is ordinary body, then quantity of radiant heat emitted by ordinary body per unit time per unit area is E sigma A T to the power of 4 minus T0 to the power of 4, where capital A is the surface area of that body.